Now that we know a little bit about RLC circuits, let's look at an RLC condition called resonance. So RCL, and recall that we looked at it before we were driving it, and we plotted we solved the differential equations for what would happen in time, and we looked at the current. Remember, it would oscillate and decay. It had this natural frequency that at which it wanted to oscillate. But then the resistor would cause the decay. It wouldn't oscillate forever. So we kind of looked at that. Now if we drive it, the differential equations lead to something kind of similar. It does have a frequency where it really wants to oscillate. So if we go back and look, Imax, the maximum, or the amplitude of the current oscillation, was Vmax over the impedance, the square root R squared plus XL minus XC squared. So you can look at this and say, well, I want the current, what's it going to be? It's going to be V over something. And you realize there's something special when these two are equal. Not that they're zero. You don't have to get rid of the capacitor and the inductor. Just when they have just the right value that they're equal, what's going to happen is, when that happens, then that's going to be 0. And when that's 0, that's the smallest value you're going to get in the denominator. Therefore, it's the biggest current you're going to get. And if the resistance happens to be small, then you're going to get a really, really big current because you get your Vmax over something small. But the maximum you're going to get is when those are equal. Let's see what that looks like. That's when omega L equals 1 over omega C. So you bring that over here and that over there, and you get that happens when omega squared is 1 over LC, or when omega is the square root of 1 over LC. But you may recall that was the frequency where this happens. That's the natural frequency. We call that omega naught usually. That's the natural frequency where this circuit sort of wants to oscillate. If you just perturb it and just let it go, it'll oscillate at that frequency. What's also true, if you drive it at that frequency, you'll get your biggest response. This is called a resonance. If we were to plot the amplitude you would get, and amplitude could be many things. You could plot power or voltage across one element or whatever. Here we could just plot Imax, right, the maximum current. Then it looks something like this. It goes through a peak, and it goes through that peak at omega naught if we're plotting versus omega. Okay. Omega naught is the resonance frequency where you get the highest current. So resonances are interesting. They can be really sharp or they can be not so sharp. The center, the position of the resonance, omega naught, depends on L and C. The width of the resonance, how sharp it is, depends on the losses. It depends on R. So the lower your resistance, the sharper the resonance you'll get.